We now give an application for the variational formula for mutual information that we saw in the previous video. So we first define this quantity called capacity of a channel, which will play a very important role later in the course. But for now, we will just define this formula. This is one of the most celebrated formula in information theory. So for a channel W from alphabet X to alphabet Y, the capacity of this channel W, C of W, is defined as max over all input distribution P on this alphabet X, the mutual information between PW. So this is the mutual information between the input and the output when the input distribution is P and the channel is W. So this is the capacity of a channel. So we can use the variational formula for mutual information here to write an alternative expression. So this is max over P. That's what capacity has. Max over all input distribution. This basically is the maximum mutual information that you can have between the input and the output of a channel. Okay, so we substitute the variational formula for mutual information here. Okay, so that is given by min over Q. Now this distribution Q is on the output alphabet. Summation over X, Px, the divergence between Wx and Q. Alright. So, and now we make an important observation. What we note is that this max and min here can be interchanged. Okay, so this is a claim. CW equals to min over Q max over P. I'm interchanging max and min of summation over X Px. This interchanging of max and min is a bit technical, and I'll justify it soon. But before I do that, let's notice the implication of this interchange of max and min. Once we have interchanged this max and min, we can continue as follows. This CW now is min over Q. That stays, but the inner max is now very easy. Since Px sum to 1 and all the terms are non-negative, what is the value of this maximum? You can pause the video and think about it. Now that you have thought about it, the answer is very simple. The best Px, the maximizing Px, is the one which puts all the mass, all the probability on the X that maximizes this. Okay, so this max is a very simple expression. It's max over all X of this guy. So what is this quantity now? This quantity is rather geometric, has a very nice geometric interpretation. Once again, we look at these probabilities W1, W2, Wx, the different probability distributions on the output for different values of input. These are distributions on the output. So just draw them as points in the probability simplex for the output. So what is this quantity here? You take a Q, some distribution Q here, and take the distance between Q and these points. These are different distances. And look at the point X that is farthest from Q. Okay, so look at that point. So in this case, visually, this furthest is in Kullback-Leibler divergence. So suppose this is that furthest point. Okay, so then this inner part here, this max thing, is exactly equal to this distance, and you are looking for Q which minimizes this max distance. Drawing parallel with basic Euclidean geometry, such a Q will be essentially what is a centroid in Euclidean geometry, and in that case, this distance, this particular minimum maximum distance, will correspond to the radius. You can think of a notion of radius of this set. Will correspond to the radius of this set. Okay, so in this alternative form, where capacity is equal to min over q, max over x, the divergence between wh and q. This thing is called the information radius. Information for information geometry, just like your Euclidean radius of a set in Euclidean geometry, this is the information radius. Okay, for this set w1 to wx. All right, so that's a very nice geometric interpretation. But how do we prove this? The critical thing in the proof was this claim that you can interchange max and min here. This changing of max and min is a very interesting question in mathematics. It has received a lot of attention in the past, and it is used quite a bit in game theory. For instance, the famous one of the famous instances of this interchange of max and min is the von Neumann's min-max theorem, where the interchange of this max and min is justified for bilinear forms, which have form A transpose. So let me put it this way. Let's say X transpose A Y, and you are minimizing over X and maximizing over Y. Okay, in this case, such a interchange of max min can be justified, and there are many famous versions of this min-max theorems. Another famous version from economics is this min-max theorem by John Nash, which leads to the theory of Nash equilibrium. Okay, so this is another min-max theorem, and in fact, when can we do this interchange of min-max? Well, when this function that we are optimizing satisfies certain technical conditions. Okay, so I'll write one version of this min-max theorem which we can use here. This is called the science min-max theorem. I'll give a rough statement because formal statement is sort of beyond the scope of this course. So suppose you have a function f and it has two inputs f, u and v, and you want to look at the minimum over u, maximum over v of f of uv. The question is, when can you interchange this min and max? One set of conditions under which you can interchange this min and max is when f is convex in u and for a fixed v, and concave in v for a fixed u. If that condition holds, then you can interchange max and min. Okay, if f is convex in u for a fixed v and concave in v for a fixed u, then you can interchange this max and min. Now let's look at this function here. So we are viewing this guy as a function of p and q. So it is clear that this function is linear in p. If you think of p as a vector, this function is linear in p. Right? It's a linear function of p, and therefore it is also concave in p. So this satisfies the second condition here. Also, this function for a fixed p is convex in q because divergence is convex in q. Therefore, it satisfies this condition as well. And therefore, you can interchange max min to min max, and that's what this claim is. So we are essentially using the science min max theorem. I'm not proving it. If you search for it, you will get a very nice Wikipedia article on this, and that is, I think, quite informative. You can take a look at that. Okay. So good. So we have this nice interpretation of capacity as information radius. How do we use this? There are many applications of this, but in the context of topics that we have seen, this can be used to further simplify Fano's inequality. Remember that Fano's inequality gave us a lower bound for probability of error for Emery hypothesis testing. It said the best probability of error, the minimum probability of error you can get for Emery hypothesis testing when the input is x, uniform distribution on x, which is taking m possible values, and output is y, is 1 minus the mutual information between x is uniform here, xy, plus 1 by log m. Alright, That's just Farnose inequality. Now I can bound it below by this quantity, because I can replace the uniform distribution with some other distribution, with the maximizing distribution which attains capacity. I'm just putting max over. So in going from this to this, I'm just putting a max over all input distribution x here. So you get this log m. But now I can use this formula for capacity. Okay, so by this formula I get 1 minus min over q max over x divergence between wx and q plus 1 by log m. But by substituting any particular q, we'll only get a larger quantity and therefore a weaker bound. So you can substitute any q of your choice. Therefore, we can substitute a q which is equal to some other x prime for any x prime, and then you can convince yourself that this bound is further, it can be further weakened to this one, wx prime plus 1 by log m. Okay. So what is this divergence between wx and wx prime? It is the distance between a pair x and x prime here, and sorry, this should be max. And what we are looking for is the max distance. So the furthest, the farthest distance between a pair here. So that distance, the largest distance between a pair here, that distance can be thought of as a diameter of the set. So we talked about information radius. This is the diameter of this set, the farthest distance between any 2 points in the set. And this is a very commonly used bound instead of mutual information. This original mutual information bound is rather difficult to evaluate in practice. So we relax it to this pairwise distance bound, divergence bound, to get a more tractable version of Farnose inequality. Okay. So to conclude, this information radius interpretation of capacity can be used in Farnose inequality and at many other places. This essentially provides a family of lower bounds on capacity. For any fixed q, you will get a lower bound on capacity. All right. This is the first application of the variational formula that we saw. In the next video, I'll show you another application of a variational formula. Namely, I'll derive Pinsker inequality from this variational formula. See you in the next lecture.